The cross or vector product. This is lesson 2 of Q502. Let's consider two generic vectors, vector A and vector B in R3 as shown here. The cross product is notated using the traditional X that we once saw in multiplication. So two vectors separated by this X is called the cross or vector product. The vector product is defined mathematically to be as follows. Vector A cross vector B is equal to this long vector here, which I do not encourage you to memorize. So, how do we find the cross product using the definition without actually memorizing this long formula? Well, what mathematicians have done is they said, well, consider a 3 by 3 determinant where we use I, J, and K in the first row, and then the components A1, A2, A3, followed by B1, B2, B3, and then we found this determinant. So, like we've done in an earlier section, we have vector I times the minor determinant of A2, B3, B2, B3, minus J, if you recall, goes plus, minus, plus, times the minor determinant A1, A3, B1, B3, finally plus K, A1, A2, B1, B2. So it's more of a process when you're finding the cross product using the definition more than it is memorization. So here we can see that this is going to be I, sorry, that's an equals, I, and then boom, boom, minus the other two, A2, B3, minus A3, B2, so on and so forth. So this gives us the I component, the J component, and the K component. So minus J dot dot dot. Unlike the dot product, the vector product is a vector, so it has a geometric feeling to it. You can visualize this, and the geometric property is that this vector, again the cross product or vector product, is a vector, and the resulting vector, so the A cross B vector, is orthogonal to both vector A and vector B. Stating that mathematically, we could say that A cross B vector dot the A vector equals the number 0, and the A cross B vector dot the B vector is also equal to 0, because we learned before that when the dot product is equal to 0, they are orthogonal. So because this is geometric and we can visualize this, I want to get a sense of this and also discuss the right-hand rule, which you may have already learned in a physics class. To explain the right-hand rule, it's going to be a little tricky as you visualize and you're not watching me but watching the screen. Place your right hand on the screen, or visualize placing your right hand on the screen, and what you're going to do as you place your right hand on the screen, you're going to point your thumb up, so the thumb should be pointing you. Now picture for a moment that you take your finger, so oh geez, how do I draw this? My hand is sort of curled and my thumb is coming out at me. And if I say A cross B, then I'm going to curl my fingers through theta from A to B, forcing my thumb to come out towards you. Okay? I don't know if that makes any sense, so it's coming off the screen. Now if I did B cross A, then I need to lay my hand straight, but the only way to let my fingers curl from B to A, I would need to be inside the computer and then my thumb would point inside, using my fingers crossing through B to A because of the order B cross A versus A cross B. So let's see if I can't put some perspective to this. Okay, so there's my A vector, and here is my B vector, and of course my theta between. Now let's do A cross B, pretending like this is this has some perspective. So to lay it flat on this plane here, A cross B, in order to do this appropriately, my hand would have to lie on top of the plane so that these fingers here that curl in will curl through A to B, forcing my thumb to shoot upward. Now that means that the cross product, we said, is going to be orthogonal to both A and B, so it's coming off the plane this way. It is orthogonal to A, so that's 90 degrees, and orthogonal to B, and that's also 90 degrees, but it's pointing upward in this case. If I'm going to do B cross A, and I'm forced to use my right hand, then my hand, if it's going to lay flat on the plane, would have to go underneath here, and it would lie flat, and then I would curl B through theta to A, then my thumb would be facing down, making the vector orthogonal to both the yellow and the purple, but in the downward. So this vector pointing up is A cross B, and the vector downward is B cross A. It also tells us that these two are not necessarily equal. So we talked about the definition, we talked about a geometric property, and now we're going to talk about a theorem. A theorem says that the magnitude of the vector A cross B is going to equal the magnitude of A times the magnitude of B times the sine of theta. And we're going to prove that later in the lesson. Prove in video. The cross product can also be used to find the area of a parallelogram formed by two vectors. So what does that mean? So we have a vector here, and we have a vector here, and if we kind of connect these to form a parallelogram, the cross product will help us to find that area. So the traditional formula for the area of a parallelogram, I'll make a vector, or sorry, make a line, an altitude, so that's perpendicular to the bottom vector. And a traditional area, let's make a theta here, we would say the base times the height. So the base here is, let's say, vector B. The magnitude of vector B would be the base, and let's just call this vector A over. So area equals the base times the height. So the base of this is going to be the magnitude of vector B, and then the height of this, using trigonometry, is going to be vector A magnitude times the sine theta, which is the same as magnitude A times magnitude B times sine theta, which by the theorem that we're still yet to prove tells us that's going to equal the cross product's magnitude. So the area of the parallelogram is simply the magnitude of the cross product, and then the area of the triangle. So if I only wanted the area of this portion here, same two vectors B and vector A, then that would simply be 1/2 the magnitude of the cross product. Another theorem here is that vectors A and B are parallel if and only if the cross product is equal to the zero vector. Now this is not a great diagnostic for parallel. We would first check to see if one is a scalar multiple of the other. That would be the best diagnostic, but this in fact is a theorem which has other utility, and I would like you to prove this theorem for homework. So if I didn't write it in the list, please add this to the list. Proof for homework, similar to the proof for the dot product. Some properties of cross products, and the best way to show this is if I make a circle with I here, J here, and K here. If I go in a clockwise direction, then the cross product will just equal the remaining one. So for instance, if I said I cross J, then that's going to equal K. J cross K is going to equal I, and lastly K cross I is going to equal J. If I go counterclockwise, this is going to be the opposite of K, this one's going to be the opposite of I, and finally the opposite of J, which makes sense because when you reverse like I cross J versus J cross I, it will be the negative, like in the right-hand rule where one points up and the other points in the opposite direction.